When we walk outside, we treat the ground beneath our feet as a permanent, immovable foundation. It feels like the ultimate definition of stability. But that solid rock is merely a thin crust. Beneath it sits a highly pressurized thermodynamic engine, continuously churning and generating superheated molten rock. Because of this immense subterranean pressure, it seems like the surface should be constantly fracturing. Yet volcanoes can spend thousands of years locked in complete silence. To understand this, we have to look at the exact forces holding that liquid rock in place, and what actually tips the scales to break the standoff. An eruption is never a random accident. It is the mathematical resolution of competing physical forces finally reaching a definitive tipping point. The upward push starts deep within the mantle. As rock melts at temperatures over 1,000 degrees Celsius, it expands. It becomes significantly less dense than the cooler, solid rock surrounding it. This density contrast creates a powerful buoyant force, pushing the magma up through the crust. It squeezes into fractures, wedging its way higher until it eventually stalls, pooling into an underground storage reservoir. This rising magma carries a massive payload of dissolved volatile gases, primarily water and carbon dioxide, trapped directly inside the melt. As the magma ascends and the crushing pressure of the deep earth lessens, these dissolved gases go through a process called exsolution. They can no longer remain dissolved in the liquid, so they separate and form physical bubbles. Inside the chamber, as bubbles nucleate and grow, the magma's density drops while its volume rapidly expands, multiplying internal overpressure. That expanding gas forces the stalled magma against the surrounding rock walls, pushing structural integrity to the edge of failure. A dormant volcano is essentially a loaded mechanical spring. The system is so tightly pressurized that it takes only a microscopic shift in the surrounding environment to release it. Sometimes that shift comes from below. A fresh surge of deep magma can inject into the bottom of the reservoir, providing the final spike in pressure needed to fracture the rock ceiling. Often, the equilibrium is broken by forces acting from above. Environmental changes on the Earth's surface can reach deep underground to uncap the system. A high-magnitude earthquake hundreds of miles away can send seismic waves rippling through the crust. These intense vibrations can shake the chamber, driving sudden bubble growth or liquefying a stiff, locked mixture of crystals and melt. Then there is lithostatic pressure. This is the immense downward physical weight of the overlying rock and glacial ice pushing back against the magma, keeping it locked in place. The upward force of pressurized magma is held in check by the massive downward weight of a continental glacier. Gradual melting removes billions of tons of weight, reducing the restraining pressure. The magma expands, overtakes the rock's threshold, and breaches. A mountain's fate is tied directly to the atmosphere and tectonic plates around it. A shifting climate or a distant fault line dictates exactly when that chamber will fail. Once that equilibrium breaks, the magma rushes upward through the conduit toward the surface. What happens next is a physical race that determines how violent the eruption will be. If the surrounding rock is highly permeable, or if the magma rises slowly, the expanding gas bubbles can escape into the crust. The magma depressurizes, flowing out safely as steady, oozing rivers of lava. But if the magma rises too fast, or if it is highly viscous and thick, those expanding gas bubbles cannot escape. They remain trapped inside the liquid rock, building extreme internal pressure as they race upward. This leads to the glass transition threshold. The pressure inside the bubbles becomes so immense that violently tears the liquid magma apart, shattering it into a supersonic barrage of solid ash. The massive scale of a catastrophic blast is decided in those final seconds of ascent. It is the result of a microscopic battle between expanding gas and thick, viscous rock. When pressure breaches the surface, the localized blast immediately expands to interact with global atmospheric systems. A major explosive eruption injects millions of tons of pulverized rock and sulfur dioxide directly upward, high into the stratosphere. Once in the upper atmosphere, these sulfur compounds convert into aerosols that act like a planetary mirror. They scatter incoming sunlight back into space, driving a measurable, temporary cooling of the global climate. Because we know eruptions are driven by pressure, we can track the signs of an impending break. By monitoring subtle ground deformation, analyzing escaping volcanic gases, and microseismic tremors, scientists can map the stress inside the chamber to forecast the next event. Eruptions function as the planet's mechanical pressure valves. They are the inevitable result of accumulated stress, a violent confirmation that the ground beneath us is constantly reacting to the immense heat and energy of the interior.